Good afternoon, YouTubers. Today I'm gonna be discussing what I'm doing about inverters, and the main idea here is to use a microwave transformer. You know, those one that you can get for a few dollars or for free. They are good for about 500 watts. So keep in mind that that's the idea, to make an inverter with those type of transformer. So basically a transformer, like, I love this picture here. Let's see if I get this to work. Yeah, perfect. This is an inverter that will convert 12 volt DC to 120 volt AC topology, and that the idea is I'm shooting for USA type of design for the what we use typically here in the Puerto Rico. And here's a transformer, and you can see that it has a center tap. And if we can get somebody that do the proper switching between these two push button, we can get sort of like a nice AC. Or either you can train a monkey to do this for a while, maybe about 40 or 50 bananas a day. You might get this to work as well, but just you start to think about animal rights and all that, and you quickly stop that. That's not a good idea. So, but that's the point. The point is that push this push button, then, I'm not talking about proper direction of the current. I'm just going with the flow so that you make a connection between this size and the ground. If you switch on this one, you will do the same on the other side and so forth. So depending on what switch you use, either the direction of the current, so you have to start sort of like an AC. How about we do something different? We use sort of like an oscillator that will do the trick, that fighting these switches, which are MOSFET. Because going back here just for 1 second, these switches will not last only maybe few few pushes, and other suddenly they will stop or they will burn out very quickly. Too much current going through them, and they're not. It's not a good idea for that. So you better use this type of switches, which are called MOSFET. And this MOSFET, if you fire them properly, you sort of start to get the idea of a proper AC output through a transformer, which is the main idea. Again, this is a center tap transformer, and so you probably this part here is already built within those transformers that we were talking about the uh, microwave transformers. You will leave the primary the way it is, but the part here, this is the 2000 volts. You don't need that at all, so you want to discard all that coil and build yourself a new one, and with a center tap. So to proper fire that one, which will be about 24 volts and so forth. So you fire that in the center, and you start to get the AC output. It's not that pretty. I mean, it's going to be a square wave output, but it will do the trick. As many YouTubers have done it, they have demonstrated that you can use a microwave transformer to make an inverter by removing the 2000 coil and installing a 20 volt coil with a center tap. The question is at what efficiency. Here is one of those microwave transformer in where the 2000 volt coil was removed and a new 24 coil with a center tap was installed. If you don't happen to have this type of transformer, I mean, there's other topology, but I want to make this video very short. These are basically some of them, like a half bridge inverter. Again, depending on which one you fire, you get the nice things about this one, this transformer, is that you don't need a center tap, so you will get the full inductance of this guy, which is good, of this side, because the higher the inductance here, the lower the parasitic current that you require, and that's very good. Because one of the things that I have, that we know, that one of these 12 volt inverter, even when you are not using it, is shooting a lot of current and it's getting the whole thing hot. And this microwave transformer will get hot. I mean, that's not, that's basically it. Another topology is a full bridge. It's a lot better. And again, here they're using like a P channel MOSFET versus the N channel MOSFET down here, and depending whether if you fire this one with this one, so current will go this way. You fire this one with this one here, current will go the other way, and sort of you get the full signal, well, the full wave, AC wave. Now, to make a story very long, very short, basically here in USA or USA territory, this is the AC wave that we have, the red one, which is about 60 hertz. If you are in Europe or another Latin American country, you might get the 50 hertz. But this is what the one we use. Actually, the volt that we use here is a little bit higher. It's about 170 because RMS here is showing 110, and I know it's 120 right now, so it's a little bit higher. Never mind, but the timing is the same because it's about 60 hertz. So a full cycle at 60 hertz means that it will take about 16,667 microseconds, and but half of that will take about 8,033 microseconds. Sorry for that. So whatever you do in terms of the timing, what we are talking here, how to fire this guy, you have to be sure that you are right where is being indicated here. Otherwise, this will not work properly. So now to do that, I'm showing here a function that is staying on for about half of a cycle, which is this shown here, and then another showing negative, which is not right. I mean, because basically it's a eventually you will see what they are, but it's not that it's going negative, but it's another ping. So I have one signal doing this and another signal doing the other half of the cycle. So I'm actually using two signals to do that, and that's the trick. So that was a short introduction. Let's go back to business now. So here we are. Let's get this better view. It's kind of intimidating at the beginning, but then very quickly you will find out what it is. Ooh, right there. All right. So yes, I'm using an Arduino to get the cycle done because basically there's a lot you can do with an Arduino in terms of making this circuit less dangerous. If something blew up or something failed, the Arduino will stop the whole thing together, and things might get better in the long run. But this is the big guy, the transformer. Again, my idea has always been to use a microwave transformer. I cannot discard it. After a few trials, everything starts to get very awful. And the problem, everybody, when I show one of these transformers, is what is inside. So let's take a look. And this is what is inside. The primary inductance is about 800 millihenry. That's this side here. Now, what is called here secondary is this side here, this one here, which is about 15 millihenry. And the problem is this: in a regular microwave transformer, this size, if you measure it, is about 200 millihenry in a 500 watt typical transformer that I have available, and they show 200 millihenry. With that said, it means that this part here we have to be a lot lower than what I'm showing here, the 15, meaning that this part here will be about 2 or 3 millihenry, and that's bad because it means that every time I fire one of these guys, whatever side it is being fired, it's gonna shoot a lot of current, which due to the very low inductance that I have on this side, and that's bad. So that's what I think most people show you that yes, indeed, you can do an inverter with this guy, but it's gonna be a very low efficiency, and it's gonna get hot, very hot. So you want to be careful with this type of transformer. Again, I iterate a little bit on them and I settle on this value. Not that they are the best. The higher this inductance here on this side, the better you are. less parasitic, but it means that the primary inductance got to go up, and and that's another problem. All itself trying to build this transformer so to accommodate properly to what we want. Now, let's see. Just to make a story short here, actually, let's close this. So everybody already know what is inside the primary DC resistance. About one, it might be a little bit higher depending on the thickness of the cable. On the 15 millihenry, point 0.2 or less could be okay. So I never mess around with this too much, and I put the coupling factor of 0.95. Could be less than that as well. So who knows? Let's say okay. Now, the next part here, you can see that I'm able to switch some caps. I mean the capacitor here if I have to, and I also can switch the load. But I also have one permanent load here, about 1K. That's for stability. Maybe you don't need that. It's just that Proteus tend to get a little bit fuzzy when the steps get too small. So it would, it would bump. So I put that 1K there just to avoid that. Now as I said, I have a lot of instruments to measure what's going on. Like for example, AC here, both the DC amount of DC current, or AC. Actually, I have it here. Is AC amps? Yeah, AC amps. Sorry, AC amps. And and I also have an AC amp here for the on and off amount of current that I'm shooting from my 12-volt battery, 12.5 actually. And here's the MOSFET. I'm using two MOSFET, and I'm also measuring the voltage that is that's going to be developed between this leg and this one for the transformer. So the closer to the twice this volt, the better. So it should be about 25 volts or so. Now this MOSFET with this transistor here, which are the one I use to fire them, you want to be careful. Here is it could be a confusion here, and it has to be with this. The way I think about this, the Arduino is trying to turn on this guy. Turn it on, it means that it have to go through this inverter to put it off, because when it's off, when this guy is off, then through this pull-up resistor, then you got this to get on. So in other words, if this is on, this side is on, but I have to go through this inverter. It's changing the polarity of the signal. Like here is 0, you get a 1. If it is a 1, you get a 0 here. Otherwise, it's gonna get very confusing. So in order to maintain the whole thing, understandable, the idea is to ensure that you have whatever is on here. It means that this guy is on, and forget about the other stuff. I add few things more into this Arduino. I add, like for example, I can, tailor a little bit the firing of this stuff within the cycle, so I can make the duty cycle longer or shorter, whatever I want. I can also, use a push button to start the action. Like for example, you can prepare some of these switches, whatever you want. Like want capacitor to be, on, or you can want capacitor to be on, and you want the load to be on when you fire them. I mean, you can do all those kind of things. The nice thing about using the Arduino is, the facility that you can change anything on the fly, basically, if you want to. And behind that, there's a powerful code. So here we are. This is the code for the Arduino. And here, this program will provide the proper timing for a square wave inverter using pin 9 and 10. To adjust the duty cycle on these pins, we use timer 1 library. Basically, that forces an interrupt every second so that we can adjust the duty cycle properly. Here is the software. They include timer 1 library with a duty cycle initial value of 1023. That's maximum. That's full time cycle or duty cycle. The value that we read from the analog point or the analog pin in the Arduino, we also set it to 1023 to start with. Now here where where you have to be careful. The timer frequency, we are talking about half of the cycle. So you remember this number comes from what we did on the sinusoidal wave, and half of that will be dedicated to one pin, and the other half to another pin. So like for example, Basically, then we go here. This is for the positive side. That's the startup process. And here's the pin mode. Pin 9 is an output. Pin 10 is an output. Pin 2 is going to be an input, just a kind of a push button. And we start with pin 9 and 10 low to keep the inverter off while we wait here until somebody push the push button to get started. Now we initialize the timer for the interrupts, and that's about 1 second. I have here 1 million microseconds, so it's equivalent to 1 second. And here is the interrupt. When it is executed, it goes to this cycle time subroutine. At this point, it's a very simple, very basic one. It's just to read the duty cycle, how much we want of that. However, as shown here, in the future, many other things can be checked, such as over voltage, low voltage on the batteries, and for voltage feedback control, you can, do something about it. However, you need for this part here for the feedback control, I will say that you need to mix this design that I have here, this inverter design, with probably with the boost converter that I talked before. Anyway, that's a long story, so keep it short. And I'm basically here in the loop is where we execute the sequence, the proper sequence to keep the signals, firing properly. Like for example, pin 9 is basically for the positive part of the signal, and this value here, like for example, if it's 1023, this will be 1. So basically you have timer frequency times 1. That's obviously timer frequency. So basically the delay is going to be about close to 8,000 microseconds or 8 milliseconds. So when it dropped to low, if you subtract this value from here, this will be 0, because basically you maintain the step of the duty cycle full on. All right, so it put wave up equals 0, meaning that we're going to do now the one for the negative part, which is identical to this one. It's not a big deal. I maintain this code as simple as it can get, so it can be easily used by anybody. So that positive side, negative side, you want to adjust the frequency, the duty cycle, you can do it. You want to adjust the frequency, then you have to go up here. But you don't want to do that. You want to keep the 60 hertz, basically. And that's basically the code. There's nothing more into it. Let's go back here to my, let's pick this. Let's see where we are. There. Now, oops, sorry for that. I'm right here, and now, without more to say, let's close. They are closed. They are closed. I like that open, and now let's fire this this guy. So let's see what happened. That's strange. Sorry for that. I didn't load the guy. So let me load the guy with my ARDUINO. So show verbose output during compilation. You need that. Very important, because that's where the hex file will be generated. So with that established on the preference, the next thing is generate. Now you can see all that wording where it goes. And now the thing is, wow, that's a lot of stuff. All right, here we go. I need for a hex file. Thank God it's at the end, so I don't have to look too deep into it. Here we go. So you need to copy all this address here up to here. So you copy that, control copy, control C, and the next part that you will do is take that address and put it into your simulation, and I show that in a second. Somehow that part was kind of I don't know, maybe because I shut off the Arduino at one point in time, so it got messed up. So let's go back to Proteus, and that will do. Here, and you put it here. It is already there, but somehow it missed it. So let's put it back. Okay. So now I got the code. Everything look good. So let's see. Oh, close, close. Now fire. Bingo. Now it's working. So you can start to mess around with it. Right now you don't see anything. Good, because obviously the Arduino is on the off stage. There's nothing is being fired. Like for example, this is off. This is off. Both pins are off, meaning that these are on. If these are on, this the voltage here is pretty much at ground, so they're not being fired at all. So to fire them, then let's push this guy, and bingo, you have the what you are expecting. So let's see what's going on here. I'm about 100. Let's see, about 100 here. If I remove the cap, get better, get lower, not good. Let's see, get it there. You can start to mess around a little bit. Now I have a sort of like a sinusoidal wave here with a very, I would say halfway uh, duty cycle in each of the pins. So let's increase the duty cycle so I can get here to about 100 and so. So let's push this up. So you step here and then you can start to see. There we go, about 100 or so. Yep, I push it and now I have my 116 volt. Perfect, about 127. So that's the amount of watt that you are consuming through that load. It's 100 ohm resistor. And so let's take a look here. What happened when I open the load? So you see that the power jumped to about 164, but very bad because there's a lot of current going through that it's not used for anything. And the problem is this cap. Get the cap out, and you can see that the wave is not that pretty anymore, but you are not wasting too much energy either. It's about, I don't know, about 4 or 5 times 12, less than 60 watts parasitic energy. So as soon as you get the load disconnected, if you don't sense current, you should then stop fighting the MOSFET to get this, properly, to reduce the amount of current going through, that is being used from the battery. Doesn't look bad, but again, when you put the cap, the current just jumped to very crazy value. So 16, that's a lot for not doing anything. Put this to work. So that's how it works, and that's how the inverter looks like. Again, the idea is to make this video short. I try to make this to work with a regular microwave transformer parameters, but I didn't like at all the results, so I leave it up to you. I know that it works, but very, very marginal. I don't think that it is. I mean, they are not meant to be used like that. They're gonna get hot, very hot, and so definitely you want to be sure that going back here. Let me stop this for actually. Should I leave it on? No, let me stop here. Let me see. Let me stop. So again, I look here at the transformer, and these are the numbers that I did use. That they are, I would say that it's a decent transformer for this kind of a, I don't know, 200. You might get to a 200 watts easily. Well, not that easy. Let me. You gotta work it out harder. Now, what makes this very cool is if you find a way to change this, and that's a boost converter. If you use a boost converter and you can change this guy to a larger value when it's required, definitely you will guarantee here your 120 volts AC. Perfect, the way it should. One last step, let's verify that yes, indeed, my frequency is right where it's supposed to. Let's say okay here, and let's fire this one again, once again. Okay, let's fire this guy. Okay, now let's do one quick here. Let's do one quick shot here, and let's use the cursor. You can read it anywhere. Let's see where we are here. There we go. Love this. So here, from here, which is 0 to here, you get 16.8. That's perfect right at the shot. 16.8 milliseconds. Could be less, could be more, but it's right. I would say I'm happy with it. So it's perfect. Now, when this is uh, low, 0 volt, then the other pin is in high by a perfect margin. So this is the square wave input for fighting the MOSFET, and you get a nice, sort of nice sine wave. Could get worse if you open here. Let's see. It's not that bad. All by the what we have here in the transformer. Actually, let's put this thing out. Sorry for that. There, I said what? Now is the way it's supposed to. That's the shape of the wave when I'm not using the cap. And again, some people will say, well, that's better than nothing. I guess I leave it. I leave that up to you. And anything else to say? I think that I have said everything. Sorry, the idea was 15 minutes. I think that I'm 20 minutes already. Have a great day. Bye.